For our final unit of the semester, we're going to talk about rotational motion. So to start out, we'll talk about equilibrium. And a concept that's important for equilibrium when we're talking about rotation is torque. So let's take a look at this pile of rocks. How do the rocks remain balanced? So these rocks are in equilibrium, and this is the kind of equilibrium that we call static equilibrium. Right, so we're familiar with this from translational motion, the type of motion we've been talking about all semester, where an object moves from place to place. Right, you can have an object have zero acceleration while sitting still, but you can also have an object moving that has zero acceleration, right, as long as it's moving at a constant velocity. So for rotational motion, we can have static equilibrium, like this pile of rocks that is not rotating at all. But we can also have dynamic equilibrium, like this wheel that is rotating, but it's rotating at a constant rate. Okay, so what are the conditions to make an object be in equilibrium? So you might say, well, to be in equilibrium, you have to have all the forces balanced. Right, and that's the first equilibrium condition. So if we look at this hockey stick, we can see that there are two forces pushing on it. So you could imagine, this hockey stick has been dropped onto the ice, and two opposing players run into it, and so they have forces that point in opposite directions. So, or maybe it's two people trying to grab this stick, and they're both pushing in opposite directions. So we see the free body diagram there. The forces balance out, so the net force is zero. Right, so we would have constant velocity. If the stick were initially at rest, it would stay at rest. If it were initially sliding in some direction, it would keep sliding in that direction at the same velocity as long as the forces are balanced. But is that enough? Here we take those same two forces and just move them away from the center of mass. So now we can see that the arrows there that are kind of purplish in color, they indicate that the hockey stick is going to rotate. But our free body diagram still shows the same picture, right? We have a force to the left and a force to the right. They balance each other out. So if the forces are offset, it's going to start the object into rotation. So it wasn't initially rotating and it starts rotating. That's not equilibrium, right? So it's not enough to just say the forces are balanced. We also have to worry about where those forces are applied on the object. So now we can't just do our free body diagrams and treat all of our objects as if they're just a simple point. We have to acknowledge the fact that objects are extended objects and can rotate. So torque is a concept that sort of takes force and moves it into the realm of rotational motion. So torque accounts for both the force that's applied to an object and the distance from the pivot point. Now, the pivot point usually is going to be given. So if we look at this picture of a door, we know that the door is going to pivot around the hinge, right, if it's going to rotate at all. So here we have our definition for torque. So torque is the lowercase Greek letter tau. And I've written it here as the force perpendicular times r. Now this is a little bit different from the way that you'll see in the flipping physics video, which I'm also going to share on Blackboard. And it's also a little bit different from the way it's pictured on the diagram, right? There, the perpendicular subscript is put on r. So what does that mean? Well, it means that not only does the force applied and the distance from the pivot matter, but it also matters what angle between r, which is called the moment arm or the lever arm, and the force vector happens to be, right? So I often like to, we're used to breaking down forces into their components, and so that's why I like to use the perpendicular component of the force, right? So in this picture, the force appears to be exactly perpendicular to the moment arm, which means it's perpendicular to the door itself. So that perpendicular component can be found by taking that force times the sine of the angle between the force and the moment arm or the lever arm. So if we want to think about how all these things combine, right, we have to worry about the force, the distance from the pivot point, and the angle. We have a really intuitive understanding of this based on understanding how we open a door. And again, you can see the flipping physics video on Blackboard for a good video illustration of this. So how would you open a door? What's the best way, most efficient way to open a door? Where would you apply this force? Well, first of all, we know that the bigger force that you apply, the bigger torque's going to be. Okay, so that part's simple. So if you're going to try to open a door, would you apply the force close to the hinge or far from the hinge? And would you apply it perpendicular to the door or parallel to the door? So you'd apply the force far from the hinge, right? So the doorknob is not just near the far edge of the door to make the latching easier, but it's also a good place to apply the torque, and you're going to push perpendicular to the door, right? So if you push parallel to the door, you'd just be pushing the door right into the hinges, and you get no torque at all. That's no way to make a door rotate. So, and you know, especially if you have a heavy door, if you tried to push it real close to the hinges, you might get it to rotate eventually, but it's going to be a lot more difficult than if you push near the doorknob at the far, make your moment arm as large as possible. And of course, perpendicular and parallel aren't the only options, but they're the sort of two extremes, right? So if you are perpendicular to the door, you can think you're not wasting any of your force, right? You're pushing it all in the way that's going to maximize the torque. But if you push parallel, you're wasting it all, right? You're not doing anything to open the door. And if you're at some other angle, you're somewhere in between. Now, the other thing that's important to note is that torque is a vector, right? So the direction is going to matter. So not only the magnitude, but the direction. So in this class, we're mostly going to be able to break that down into whether the torque would cause a clockwise rotation or a counterclockwise rotation. Now that's a little bit ambiguous because if somebody were looking at the door from the opposite perspective, they would disagree on which direction is clockwise or counterclockwise. But you can solve that by just having a diagram to refer to. So you have to pick one of those directions to be positive, right? Either clockwise or counterclockwise is going to be the positive direction. And generally in math, we take the counterclockwise direction to be positive. So you can see here in this diagram, there's two, you'd have the same torque in the two pictures in terms of magnitude. But because the force has flipped direction, it's going to change the direction that the door would rotate, right? So in the picture that's on the left side, you get a counterclockwise rotation, which is a positive torque, and in the other picture, you get a clockwise rotation, which is a negative torque.